I'm Walter Waddell, co-chair, and have the pleasure to welcome you back this afternoon to the International Tire Exhibition and Conference organized by Rubber and Plastics News. Our next speaker is Dr. Sujith Nair from ExxonMobil Chemical Company. He earned his PhD in chemical engineering from the Pennsylvania State University, was awarded a Pacific Northwest National Laboratory Fellowship for his work on conductive nanofiber coatings. Sujith was a senior research engineer at Millikan, where he led projects pioneering products in ballistics and high-performance fibers, in coated release liners and films, and in reinforcements for ultra-high tire performance. At ExxonMobil, he started in new product design and application development in the specialty elastomers and butyl group. He has 20 publications and 10 United States patents on polymers, reinforcements, and compound-related inventions. Currently, he is a market developer in butyl polymers and will present evaluation of X-Pro 3563 in tire Innerliner applications. And now, Dr. Sujith Nair.
Thank you, Walter. Thank you very much for the introduction. Good afternoon, everyone. I would like to start off with offering my deep sympathies and prayers to everybody who has been directly or indirectly affected by the COVID-19 crisis. I know that this is a difficult time for all of us, but I'm sure that at some point we will leave it behind us and we'll emerge out of this stronger than ever before. So again, I welcome you to the presentation. Very happy here to be at ITEC. This is new for all of us. So, thanks to digitalization, we are now able to, meet and fulfill our commitments better than ever before. So going virtual is one of the most new things that's happened, especially this year with most of the conferences. So I thank you for your time. Thank you for being here and attending my presentation. So what I'm going to do in this presentation is talk about one of our newly commercialized products, which we have targeted specifically for Innerliner applications. This is our X-Pro family of polymers, and the grade that we are targeting for these applications is X-Pro 3563. So what I'm going to do in this presentation is first talk about some of the automotive megatrends, and then some of the industry challenges. Then we'll go into what affects air retention. So what are the parameters that actually significantly affect the air retention? We'll talk about that. We'll go into the product, show you the chemistry on how the chemistry is changing. And then we'll talk about some of the basic compound properties. And then we'll take you through a factory processing trial where you can actually look at the advantages that X-Pro provides over the incumbent materials. So talking about some of the megatrends and industry challenges, one of the things that has been very evident and unstoppable today has been the advent of electrification. Previously, before 10 years, very few vehicles were fully electric. It was mostly plug-in hybrids. But now you've got the electrification happening in a full-blown mode. It's become almost like the thing of today, right? So back in the day, you would have 2 or 5 models which were fully electric. In 2020, it is said that there's around 400 new EV models that's being introduced into the market by several OEMs. So that's a huge number. So if you look at the light vehicle fleet, we see that over the years, electric vehicle fleet has continued to grow. We predict that by 2040, a good piece of the total light vehicle fleet is going to be fully electric. Now, the other things that's actually going on with electrification at similar speeds has been what we call as the CASE phenomenon. It's connectivity, autonomous, shared, and electric. So, as you know, back in the day, automotive companies used to do innovations in-house mainly, but now you've got software giants, you've got the big companies actually stepping into this game, at the forefront of digitalization and connectivity. So you've got the connectivity aspect, you've got most of the OEMs, most of the majors also working on fully autonomous vehicles. Uh, we have had multiple different concepts and companies come up that actually have propagated the shared concept as well. And then, as we talked about in the previous slide, electrification continues to grow. So we see these disruptive trends as an opportunity. Why? Because the more you have requirements from these vehicles, so if you want to make it more connected, autonomous, shared, or electric, these are going to bring in requirements for every component of the vehicles. And along with these requirements, there is a lot of scope for innovation in new materials. So that's basically what we see. Some of the themes that actually emerge, as needs has been, energy efficiency, decarbonization, more emphasis on a circular economy, uh, and then basically more emphasis on comfort and autonomy. So basically, if you look at decarbonization, again, you want to lower the weight, you want to use much more energy efficient vehicles, materials. You want to basically maximize the lightweighted concept here, right? If you look at the circular economy, you want to be able to maximize the recycling and the reusability of these materials to reduce waste. And then as you go into autonomous vehicles, you want to make sure that it is safe, it is reliable, it is comfortable, and it's durable, right? So these are some of the needs and the solutions that we see. Now, as a company, we have been involved in various different materials that actually improve the efficiency of automotive components. So some of the materials that you must have heard from us in the past is Santoprene thermoplastic vulcanizate. And basically, we have a lot of automotive components that uses Santoprene. It's one of the ways to actually reduce the waste and make the process more efficient. So as we look into EVs, we are looking into reducing weight, we are looking into maximize the efficiency. We see a lot of opportunity for our Santoprene TPVs. Similarly, one of the components that obviously has to be optimized is tires. Make it more efficient, make it more lightweighted. So we see any material that can actually add benefit to tires, we see that as an opportunity too. And Expo 3563, we believe that it adds value to the tire because it can actually minimize air loss, better than much better performance than the incumbent bromobutyl materials. And we think that this is going to be extremely important for electric vehicles, for the reasons that we'll explain in the coming slides. So if you look at the energy dissipated from tires in a conventional combustion engine, the energy dissipated due to tires is around 7%. Now, because the electric motor is extremely efficient, and it's the efficiency of the electric motor is almost 3 times that of a regular combustion engine. So combustion engines, somewhere between the 20 to 30%. Electric engines is obviously much higher. It's like 80, 90, 95%. So basically, the energy dissipated due to tires is around 3 times that of the combustion engine. It's around 20, 23%. So the more materials we can introduce to actually minimize this, the better the efficiency is going to be. So the whole emphasis is how can we actually reduce the dissipated energy in tires, and obviously one of the ways is rolling resistance, right? So the more we can actually reduce rolling resistance, the better it is. And by rolling resistance, we not only mean the rolling resistance at the beginning, the rolling resistance for new tire, but we also mean the rolling resistance over a period of time. So basically, we believe that if you have better materials, if you have materials that can reduce your permeability or improve your air retention, that's going to indirectly affect your rolling resistance over a period of time. Similarly, in the past, we had vehicles that were used only 5% of the time. Why? Because we drive to work, we leave the vehicle parked for 8 hours, we come back, then we probably go out in the evening again. So literally for most of the day, the vehicle is standing in a static mode. It's idle. That's changing with the advent of all the shared concepts. and with obviously connectivity and autonomy, we're going to see a much larger usage of vehicles. So imagine that if you had the full of all the light vehicles going into a fleet model, then you're going to basically have much more usage of these vehicles. So it's going to probably run 80-90% of the time. And what happens is that puts additional stress on the tire. So in an idle form, the tire, there is a certain air loss in a tire in a static mode. We have seen through experiments and our own research that if you go to a dynamic mode, the more these tires are used, the more these vehicles run, the air loss is going to be around 1.5 to 2 times that of a static mode. So let's say the static mode, the air loss is 2% or 3%. In a dynamic mode, this air loss is going to be 4 to 6%. So the more the vehicle is going to be used, the more the air loss is going to be. So we believe any material that can offer better air loss performance, maintain the air in your tire, we believe that is going to be a very a possible opportunity for improvement. So now let's just dive into the inner liner, the tire, what it does, and all those aspects. So the inner liner, which is the inside part of your tire, is responsible for keeping more of the air inside, most of the air inside your tire. Right, so there is a thin layer of rubber, and this is made from bromobutyl, chlorobutyl, or bromobutyl blended with several other elastomers. So some of the requirements for this layer in order to actually give a good performance in the tire is material stability. It needs to have a good shelf life. It needs to be consistent in manufacturing. It needs to have a good adhesion to the other layers of the tire, so good bonding. And then, as far as performance is concerned, the most important function that an inner liner should provide is give a low permeability. That's how you basically prevent the air from actually seeping outside your tire. Apart from this, it also needs to have a good crack resistance, needs to have some amount of heat resistance, and it needs to have a low heat buildup. So these are sort of the requirements for inner liners. So what are the factors affecting air retention? We think that there are 3 primary factors that affect the air retention, and almost all of them has to do with the composition and design of the inner liner. So basically, if you have the best composition that you can possibly have, and if you have the best design, which means a better thickness and a better toe distance, then it should give you the best performance. So let's look at the 3 main factors that will govern the air retention aspects of a tire. So the first one is material permeability. So the better rubber you use, the lowest permeability rubber you can use, the better your air retention is going to be. For example, we have done a couple of different experiments where we have done multiple different compositions. So for example, let's say you use a blend of bromobutyl and natural rubber, an 80-20 blend, which is commonly used in the industry, versus you go towards 100% bromobutyl inner liner, we see an inflation pressure loss reduction of 30%. So the inflation pressure loss reduction, or IPLR, is a terminology that's used to actually measure the air retention performance of a tire. And what it means is the percentage of air lost from a tire in a month. That's basically what the IPLR is. So the lower the IPLR, the better the performance. So we have seen that if you just go from a composition of 80-20 bromobutyl natural rubber to 100% bromobutyl, we see that there is a 30% reduction in IPLR, which is very significant. Now, if you go the other side, let's say you say that I'm going to increase the thickness of my inner liner and I'm going to make it better. Yeah, it's doable, but you can increase your thickness by around 20% and you still get an 18% reduction in the IPLR. So please compare this to the earlier part where we actually changed the material composition. We were able to get a 30% improvement, whereas by changing the thickness by 20%, you're going to get an 18% IPLR reduction. Similarly, another parameter that actually governs the performance, the air loss performance in a tire, is the distance from which the inner liner ends in the tire to the toe of the tire. So the more this distance is, so let's say that the inner liner ends very, very close to the toe, you're going to get the best performance, right? Because you won't have air leaking through the spots where you don't have inner liner coverage. So the more closer to the toe, the better it is. Now, if you go farther away from the toe, your IPLR will be pretty high and your air retention performance will be poor. So we tried an experiment where we went from 20 millimeters, so 20 millimeter distance of inner liner ending to the toe of the tire, to 10 millimeters. So you're going more close. And we saw that there is a 10% improvement in the IPLR. So the bottom line is, from all these, you can see that there are multiple ways to actually improve the air loss performance, but the best way, the most impactful way to actually change or improve the IPLR is by using a rubber with the lowest permeability. So improving the material composition. That's what's going to give you the best IPLR. So now let's talk in general about what are you going to get with XPro. So yeah, we have bromobutyl, we have chlorobutyl. People have been using this for a very long number of years. And so what does XPro bring to the table? Number one, it's got superior air retention. So the air retention performance, the permeability of XPro is significantly better than the incumbent bromobutyl. So with superior air retention, you're going to get low inflation pressure loss rates, and you're going to get low intercarcass pressures. So low pressure buildup in your intercarcass layers. It's also got superior resistance to heat as well as ozone. So and we'll go into the reasons for why it has a superior resistance, but it's got very good resistance to aging and ozone. Now, because the performance, the functional performance of XPro is better than bromobutyl, you can also think about it as a avenue to lightweight your inner liner. So let's say you have an inner liner that's 1 millimeter thick. XPro has much better performance than bromobutyl. So you can think about, okay, now this is an opportunity for me to actually lightweighten my inner liner, go from 1 millimeter to maybe 0.8 millimeters. Some of the other advantages of XPro also is better liner handling. So it's got much better green strength, uncured strength. It's got lower shrinkage, and so better dimensional stability. And then one of the final points is that XPro has a very good affinity towards carbon black. And because of this, you get much better dispersion of black in XPro, which we will also show you in the forthcoming slides. So going into XPro, we'd like to say that XPro is probably the specialty elastomer available today with the lowest permeability. Looking at the chemistry of XPro, so again, butyl is basically a polymer, that's made from isobutylene and isoprene. So it's basically a isobutylene co-isoprene polymer, right? In XPro, the difference is, instead of using isoprene, we replace that isoprene with something called paramethylstyrene. You do a carbocationic polymerization, you get the XPro backbone. So you see that big, bulky, pendant aromatic group there. That is the difference between bromobutyl and XPro. Now, we do a bromination, and basically we get a brominated polymer. So this is what we call the isobutylene coparamethylstyrene polymers. You can go through various references in the past, and you'll find that these are also called brominated isobutylene coparamethylstyrene polymers, which is also called as BIMS, B-I-M-S. So this is the structure of the polymer. Now, a couple of things that you have to note in this is that the chain is saturated. There is almost no double bonds in the main chain. That is one of the biggest advantages of XPro. So if you look at butyl, you will still find some amount of saturation because of the isoprene in butyl, and that's important because that's necessary in order for the material to cure. But in XPro, you've got bromine on that paramethyl group, that paramethyl group in the styrene block. That's where it cross-links. So literally, you don't need to have any kind of unsaturation in the main chain in order to actually cross-link XPro. So that's one of the biggest advantages of XPro, is fully saturated backbone. It basically is very resistant to heat and ozone, just because there is no point to cleave this. It maintains all the advantages of the butyl material, but it also gives some other advantages. So the pendant PMS ring, so you got this bulky PMS group there. Two things that it does is it actually reduces your free volume, and it also reduces your segmental mobility. So what does that mean, right? Reduction in free volume means an increase in TG, and basically that's how you get your lower permeability. Now, basically, you've got lesser space for the material to actually go. It's more tighter, more tortuous, and so your permeability goes down. Also, the segmental mobility of this bulky group is much lower, and hence it's difficult for air molecules or oxygen molecules to pass through this. So we have seen that the permeability of XPro is significantly better than bromobutyl, and we'll show you some results for that as well. We already talked about the fully saturated backbone, no double bonds in the main chain, gives it very good resistance. And then the other thing is that all the cross-linking happens through that CH2Br moiety that's on the bottom of that aromatic group. And that's how you get your cross-linking. So what happens because of this is you can actually have an avenue for a very flexible cross-linking. You can cure the material without sulfur. You can cure it sulfur-free. So that's what we call clean cure systems. And that's possible too. So let's look at some of the basic compound properties that we have between XPro and bromobutyl. We use a standard ExxonMobil formulation, use 60 parts of black, 8 parts of oil, 7 parts of resin, 4 parts of the tackifier. And in this case, we have used similar curing systems. It's a zinc oxide, MBTS, stearic acid, sulfur-based cure that we have used. But again, as I said, you can cure it fully sulfur-free. You can use resins to cure it. If you want to speed up the cure a little bit, there are multiple ways to actually do that. So going into the first and foremost important property that we think, as far as Innerliner is concerned, it's the permeability. So as you can see, XPro 3563 has a 20% improved permeability over bromobutyl. So that's one of the key points that actually differentiates XPro from bromobutyl is this lower permeability. And as I said, the reason for this lower permeability is the lower segmental mobility of this bulky aromatic PMS group and the lower free volume, so increase in TG. Both of those things combined, it helps you reduce the permeability significantly. Now, the other thing that we said earlier is that, again, XPro is a fully saturated molecule. There's no unsaturation, no double bonds. And so, as you can see in the torque curve that's shown on the right-hand side, you can see that XPro literally does not have any reversion. So as you basically cure the polymer, it gets overcured, and then you have degradation because of the cleavage of these double bonds in bromobutyl. That's the dark blue curve. As you can see, the green curve, XPro 3563, there is literally no reversion because there is no cleavage points. And the cross-linking happens mainly because of the CH2Br moieties. This is a bimodal AFM image of bromobutyl compared with XPro. I've shown a low magnification and a high magnification. You can see that XPro compounds have a much better dispersion. So on the right side, you have XPro. On the left side, you have bromobutyl. Both in the high mag and low mag, you can see that the carbon black particles are much better dispersed in XPro than bromobutyl. So basically, we think that this actually gives in multiple different properties. Of course, it helps the permeability part, right? Basically, it's more dispersed, it's better. It also gives uniformity, better consistency, and it also gives better reinforcing properties. It also helps in actually improving the fatigue to failure, the crack resistance, overall mechanical properties in general. One of the other things that we have noticed with XPro is because of the affinity to carbon black, just because it acts as a better filler, it gives much more reinforcement properties than conventional bromobutyl. We have seen that XPro actually has better green strength, better uncured strength than bromobutyl, filled compounds. So this is important because it actually enables better or easier processing before it goes into a tire and it's cured. And so it's got around 25-30% improved green strength as opposed to bromobutyl. The other thing that we observe is when you go into liner sheeting, when you do calendering operations at high temperatures, bromobutyl tends to shrink in the machine direction. This shrinkage is around 20-25%. It shrinks in the machine direction and expands in the width direction. Well, what we have seen with XPro is that the shrinkage is extremely small because of the tightness of the polymer and filler, and it prevents any kind of mechanical distortion under heat for the XPro polymer. So the shrinkage is much lower, which means that it's got better dimensional stability. Just looking at compound properties in general, rheological properties, if you look at the Mooney, it's very similar. XPro probably has a slightly higher Mooney than bromobutyl because the inherent viscosity of the polymer, the inherent Mooney of XPro is around 2 to 3 points higher than that of bromobutyl. So you're going to see that in your compounds as well. Plus, you've got this good reinforcement between the filler and the polymer, and that adds to a little bit of Mooney as well. But there are multiple ways to actually reduce this Mooney and make it equal. The MH minus ML is slightly higher for X-Pro. The T90s for X-Pro in this particular curing system is twice that of bromobutyl. But as I said, there are multiple different ways to actually equalize the T90s. One of the common ways that we actually tell people to do is add a little bit of Voltac, and you can basically fasten your T90 much to a great extent. So if you look at the green compound properties, obviously X-Pro has a much higher green strength than that of bromobutyl. The shrinkage is much lower. If you look at the mechanical properties, most of the mechanical properties are almost the same. Basically, hardness is slightly higher. The tensile strength is almost same. The elongation to break is also similar. One thing that actually distinguishes X-Pro, and we touched on this a little earlier, is the heat aging properties. So as you can see, bromobutyl, when you perform heat aging, in this case, we have done it for 7 days at 125C. You can see that the strength of bromobutyl always drops, so it starts degrading. So the more you age it, the more bromobutyl degrades. Whereas in case of X-Pro, it maintains all those properties. So you can see that the change in tensile strength of bromobutyl was around 28%. It's 28% reduction in the tensile strength of bromobutyl, whereas in the case of X-Pro, it's equal or slightly higher, because there's obviously a little bit of uncross-link parts that keeps on cross-linking. But in case of X-Pro, we have always seen that the mechanical properties are maintained. Similarly, you can see that the fatigue to failure of X-Pro is around twice that of bromobutyl, and the permeability is around 20% lower. So basically, almost all component properties are equal to that of bromobutyl, and obviously you have some advantages with respect to permeability, green strength, fatigue to failure, and composition. So now what I'd like to do is take you through a factory processing trial that we did, and show you some of the advantages in processing and the final air retention performance of the tire. So in this case, we have done the mixing on an F270 machine, both the non-productive and the final. The liner production was done using both calendering and extrusion. I'll show you some specific examples of the extruded liners. Cushion was included in all cases. And in PCR, the tire size that we are talking about is a 205, 55, or 16. The splice used was an overlap splice, and the building was done on a dual stage machine. The Innerliner target gauge was around 0.9 millimeters, and that's where most of the Innerliners landed. And basically, we have also done some statistics on all of this. The mixing procedure that we use is the standard in the industry. So one thing that I'd like to point out before going into this mixing is that X-Pro will mix the same way as bromobutyl mixes. So if there is a specific mixing pattern that you're using for bromobutyl, you don't need to change anything for X-Pro specifically. This is one of the mixing procedures that we have used as a standard, and we have used this for all the polymers. So we have a two-stage mixing. One is a non-productive, one is a final, and basically the non-productive in a big Banbury in a F270 machine, we mix it for around 3.5 minutes. We normally go by the dump temperature. So we recommend a dump temperature of 135 to 140 degrees C for the non-productive batch and 100 for the final batch. But again, the reason why we picked 135, 140 is because this was what's used in bromobutyl. So we don't like to go above this temperature for bromobutyl. But as I said before, X-Pro is extremely resistant to temperature. So we have had customers coming and asking us, can I go higher in temperature? Can I go to 150 or 160? And the answer is yes. With X-Pro, you can go to 150 or 160 or even 170. There's no problem. And we have done this, and we have proven that actually the properties are even much better. So you can definitely go to higher temperatures. In this particular experiment, we have just used this as a standard. So looking at the mixing fingerprints, again, X-Pro processed the same way as that of bromobutyl. So two things that we look for, because we are actually dumping based on the temperature, is the mixing power and the mixing time. So we look at the mixing power because we want to see whether the material took similar, equal, or lesser power than that of bromobutyl. In this case, again, the mixing power was pretty much the same. So we can say that the mixing is very similar to bromobutyl. Now, The mixing time was also very similar. We are again dumping based on temperature, and this shows that X-Pro has almost the same mixing characteristics as that of bromobutyl. I talked a little bit about the shrinkage. So again, bromobutyl tends to shrink in the machine direction and expand in the width direction. And this is not desirable because, again, this shows that the material does not have good dimensional stability. So in case of bromobutyl, the shrinkage is around 20-25%. In case of X-Pro, the shrinkage is around 7%. So much more better dimensionally stable than bromobutyl. These are two sheets. The left side is bromobutyl and the right side is X-Pro. These are extruded sheets. And you can see that the surface aesthetics of both bromobutyl and X-Pro are very similar. It looks very similar. You can make it blister-free. There's no waviness. There's no nerviness. Extremely similar performance as far as aesthetics is concerned. Now, this is a splice, uncured splice figure for both bromobutyl and X-Pro. Bottom line is that, again, there is no significant difference in the splicing behavior of bromobutyl and X-Pro. It splices almost exactly the same. And in both cases, the uncured splice and the cured splice was better in both bromobutyl and X-Pro. And then finally, this is the inflation pressure loss rate results of bromobutyl and X-Pro in two different formulations. If you look at the first bar, it's a bromobutyl natural rubber formulation 80-20, which is standard in the industry. If you use X-Pro instead of bromobutyl 80-20, you get like 15-20% improvement in your IPLR. Similarly, if you compare X-Pro 100 PHR to the bromobutyl 100 PHR, you again see this 15-20% improvement in the IPLR of tires utilizing X-Pro. Now, one thing that I told earlier is that X-Pro not only allows you to get better performance. Yes, if you keep the gauges the same, your performance is going to be better. But one thing that X-Pro allows you to do is lightweight. So this is the result, the IPLR results from a TBR trial, a tuck and bus radial tire, where you can see that the inflation pressure loss rate of an X-Pro based tire is around 17% better than the bromobutyl based tire at the same thickness. Now, what we did was we actually reduced the thickness by 20%, and you can get almost a similar or better performance compared to the bromobutyl 22. So bromobutyl 22. So you can see that X-Pro 3563, there is a potential to down gauge, and this becomes more important in larger tires such as TBR. This is 11R 22.5 trial that we did, where the inner liner thickness was around 1.5 millimeters. Weighing like a couple of kilograms, right? 2.5 kilograms. So imagine that you're able to save like 500 grams in a 2.5 kilogram inner liner, a tire with a 2.5 kilogram inner liner. That's significant. So that's basically what X-Pro allows you to do. So in summary, you can see that the impermeability of tires using X-Pro, the air retention performance is around 20% better. In some cases, we have even got up to 30% better. The crack resistance of X-Pro based polymers is much better. The fatigue to failure is much better. The heat resistance is much better. And the heat buildup resistance is much better. The shelf life of X-Pro is around 3 years, so it's more than that of standard bromobutyl use, but it's got a great stability. You can see that there are a lot of superior performance advantages. So just to summarize, right, we believe that air retention will play a much more critical role in the future, especially with the advent of EVs, right? So we believe that improved air retention will provide a significant value to our end users. High PMS X-Pro, so X-Pro 3563 in particular, it provides a step change in air retention, and it also provides several other advantages as far as processing these are concerned. We believe that consistent in-use performance is going to be more and more important with electric vehicles, with vehicles going towards full fleets with autonomous driving, because again, it's a safety factor, right? The more you lose air in your tire, the more susceptible it is to catastrophic events. So we believe that improving the air retention, as a polymer supplier, as a material supplier to the tire industry, where we have supplied the tire industry with bromobutyl, we believe that this is our effort to actually improve the polymer, the polymer advantages. We see this as an opportunity to actually making a step change in this area. So with that, once again, I'd like to thank you very much for spending time to attend my presentation. My details are given on the slide. You can always call me or send me an email if you want to know more about the product. And if you want to even discuss general tire challenges, new areas emerging in the tire industry, I am always looking forward to a good discussion. Feel free to give me a call or an email if you have anything on your mind with respect to this industry or this product. And thank you once again. Thank you very much. And I hope to see you soon next year. Walter, back to you.
Thank you, Sujith, for your very interesting presentation. I would also like to thank you, our audience, for attending this session of iTech and for our sponsors for supporting iTech Virtual 2020. If you want to revisit this session or any others from the conference, they will be available on Rubber and Plastics News website, rubbernews.com, after this event is completed. If you would like to purchase papers from this or other sessions of iTech, visit itech-tireshow.com to do so. Also, you can connect with your colleagues here through the virtual networking program, which can be found in the lower left-hand side of your screen. Simply click the Meet icon to start connecting with fellow iTech attendees. Again, thank you all for joining us this afternoon. Goodbye.